Okay, so we're going to look at this series first. We're going to start with a couple easy examples in this video, and then in the next video we'll do some more complicated examples to actually see how we can do these with, well, just more difficult problems. Alright, so this first one here, clearly it's alternating. Because of the negative 1 to the k. So the first thing is we apply the alternating series tests. So on these problems, you're always going to have to apply two tests, but the first one you always apply is the alternating series test. And so we look at the limit as k goes to infinity of negative 1 to the k over k. And well, we can think of, well, what does negative 1 do as you go to the k as you go to infinity? Well, this is just going to be plus or minus 1. I don't know which one it's going to be, but it's plus or minus 1 times the limit as k goes to infinity of 1 over k. But clearly, what does 1 over k do? That goes to 0. So this would be equaling to plus or minus 1 times 0, which of course is 0. So then by alternating series test, the series converges. Okay, now star this. Now we have to determine if convergence is absolute or conditional. Okay, so then what we're going to look at is we're going to look at the sum from k equals 1 to infinity of the absolute value of negative 1 to the k over k. But what do we say the absolute value really does? Well, if I think about this for a second, k equals 1 to infinity, if I look at the absolute value of the negative 1 to the k, that's just going to give me 1 over the absolute value of k. But then if I think about this for a second longer, this is the same thing as just k goes from 1 to infinity of 1 over k. Why is it the same thing? Well, what am I substituting in for k? Positive numbers. So the absolute value of positive numbers is just the number. So I don't really even have to write the absolute value down anymore. Alright, so that's what I get. So now that I have this series, we apply tests from 8.3 to 8.5 to determine if series converges. You can no longer use alternating series on this because it's not alternating. You have to use another test. Well, it's not necessary to do this, but I'm going to go ahead and write all the tests out we have again. Geometric, telescoping, divergence, integral ratio and root. Now, to me it's pretty obvious which test we should use, but let's just go through the list here. It's clearly not geometric, so I can cross that off. It's also clearly not telescoping, so I can cross that off. It's not to the k power, so I can cross the root test off. And then if I think about it, divergence, 1 over k goes to 0, which that doesn't tell me anything with the divergence test, so that's gone. So I'm left with integral and ratio. If I applied ratio test to it, you could, but you're going to get inconclusive. So taking out the ratio test, and if I think about it for a second, integral test would be easy because I'm integrating 1 over x, which is just natural log. So the test we're going to use here is the integral test. And so then what do we have here? Well, we're going to look at the integral from 1 to infinity of 1 over x dx. And yes, we've actually already done this one in class before. This is equal to the limit as b goes to infinity of the integral from 1 to b of 1 over x dx, which this is equal to the limit as b goes to infinity of the natural log of x from 1 to b, which would be the natural log of b minus, oops, come on, erase here for me. And it's not wanting to erase here. There we go. Forgot to write my limit, so this is equal to the limit as b goes to infinity of the natural log of b minus the natural log of 1, which we know the natural log of 1 is 0, and then this just goes to infinity, because we know the natural log goes to infinity. So this series diverges. So original series, well, let's go back here on this problem here. The original series we know converges because the alternating series test tells us that it converged. But then when I looked at the absolute value, I got that the series diverged. So that means that the original series, sum from k equals 1 to infinity of negative 1 over k, converges conditionally. And then we're done with the problem. So on these problems we are often going to have to apply two tests. The first test you always apply is the alternating series test, and then the second test you apply is, well, you don't apply the alternating series test on the second part, you apply one of the other 6 tests that we have here. So let's look at another easy example just to kind of get our feet wet on these alternating series problems. Let's look at the sum from k equals 1 to infinity of negative 1 to the k over k squared. So again, clearly this is alternating. So by alternating series tests, we can look at the limit as k goes to infinity of negative 1 to the k over k squared. Which this would be equal to, again, plus or minus 1 times the limit as k goes to infinity of 1 over k squared. And then of course 1 over k squared, that just goes to 0. So this would be plus or minus 1 times 0, which is 0. So by alternating series tests, the series converges. Alright, but now we have to look at whether it converges conditionally or absolutely. So again, what we need to look at is the absolute value. So we're going to look at the absolute value of negative 1 to the k over k squared, which I'm going to skip some of the stuff we talked about in the last example. We just get the series of 1 over k squared, because the negative 1 clearly just becomes 1, and k squared is always going to be positive anyway, so I just leave it as k squared. I don't have to write the absolute value down. Alright, so I'm going to look at this one, and just like in the previous example, you can go through all the tests, and this is actually, again, just another integral test here. So I'm going to look at the integral from 1 to infinity of 1 over x squared dx, which is equal to the limit as b goes to infinity of the integral from 1 to b of x to the minus 2 dx. And again, this one's easy to integrate, or it should be for us at least. This is equal to the limit as b goes to infinity of the, well, I'm doing the integral, negative x to the negative 1 from 1 to b. So this would be the limit as b goes to infinity of negative 1 over x from 1 to b, which would be equal to the limit as b goes to infinity of negative 1 over b minus 1 over, negative 1 over 1. And then of course as b goes to infinity, 1 over b, this goes to 0, and you're left with 1. So the integral converges. So series converges. But now let's think about, again have to go back to the original problem. So original problem, I was given an alternating series here, and we know that the alternating series converges. What we're trying to determine is if it converges conditionally or absolutely. So that's when you look at the absolute value of the series. And since the absolute value converged, and it kind of makes sense since the absolute value of the series converged. So the original series sum from k equals 1 to infinity of negative 1 over k squared converges absolutely. And as I said, it kind of makes sense that we say it converges absolutely because, well, the absolute value of the series converges, so it converges absolutely. Okay, let's look at one more quick, easy example, and then in the next video we'll look at a few more challenging examples on this absolute and conditional convergence. So we're looking at the series from k equals 1 to infinity of k to the k, negative 1 to the k over k factorial. Now I claim this one is easy here, but it might not seem like it is at first. So this is clearly alternating series. So I'm going to look at the limit as k goes to infinity of k to the k, negative 1 to the k over k factorial, which we know this is going to be plus or minus 1 times the limit as k goes to infinity of k to the k over k factorial. Now this is where you might say that this is actually difficult to do, but I claim this is an easy limit. And you might say, it's not an easy limit, we haven't talked about factorials. Well, I'm going to show you why it's an easy limit here. We're going to talk about, and we've mentioned this before, growth rates. Remember what we talked about here is we said that polynomials, and I'm going to put much less than, that's why the double less than, exponentials. So, you know, we have like x, x squared, x cubed, so on and so on, much less than e to the x or even 2 to the x. We almost always see e to the x, but any kind of exponential. So that means the exponentials always beat out the x's here. But then these are much greater than, and I'll put it up here too, logarithms. So natural log of x, or just log of x, any of those. But then let's go to the other end. Exponentials actually grow much slower than factorials. So factorials beat exponentials. So I'll put k factorial, although maybe I should write x factorial since I'm doing everything with x here. But then factorials are much less than, and I don't know a way to write it other than x to the x or k to the k. So what does that mean here? Well, that means that we have plus or minus 1 limit as k goes to infinity of k to the k over k factorial. Now, when we talk about growth rates, it sounds a little weird to say it because you never reach infinity, but I'm going to say this reaches infinity first. So since that reaches infinity first, this limit is plus or minus infinity, which really means the limit doesn't exist, but it goes off to an infinity. It just keeps getting bigger. It doesn't go to 0. Now, if I had this fraction flipped, if I had, let me just put it here, if I had k factorial over k to the k, this would go to 0 because the k to the k reaches infinity first. So, since the limit as k goes to infinity of negative 1 to the k, k to the k over k factorial does not equal 0, it almost looks like a 6, does not equal 0, the series diverges, and there is nothing left to do. Alright, so this is the end of this video, and as I said in the next video we're just going to do a couple more alternating series problems, but we're going to do them with a little bit more challenge involved in them.